Welcome back to the deep dive, where we take the hardest science and basically give you the shortcut to expertise. Today we are deep diving into the sun specifically, one of the oldest, most perplexing questions in solar physics, the coronal heating problem. So here's the basic idea. The sun's surface, right, the photosphere, it's hot around 500 degrees Celsius. You'd think the atmosphere above it would, cool off further out, but the corona, the outermost layer, it suddenly explodes to multi-million degree temperatures. It kind of throws thermodynamics out the window.
It really does. It's an astronomical mystery that's puzzled us for decades. We're pretty sure this heating has to be non-thermal and magnetic in origin. Just to give you a sense of the scale here, balancing the radiative losses in the chromosphere alone, that's a layer just under the corona, that requires a huge energy flux. We're talking 106.7s, maybe 107 text erg, text under 6.
Oh, wow. Okay. That's immense.
It is, and even the corona itself needs a constant top-up, something like 104.4 to 106 attentich text erg.
So yeah, massive energy delivery needed, and historically there have been, two main competing theories. You've got magnetic reconnection on one side, this idea of constant tiny explosions.
Nanoflares.
Nanoflares, yes. The theory suggests they're about 1024 ergs each.
Okay, 1024 ergs sounds like a lot.
It does, but when you calculate the total energy needed, you realize you need literally billions of these tiny flares happening every single second, just constantly popping off. And the problem is, they're just too small. They're below the noise threshold of our current instruments, so we can't directly confirm if there are enough of them. That non-detection is a bit of a sticking point for that theory,
Right, which naturally brings us to the other main camp waves. So our mission today is to deep dive into this magnetohydrodynamic wave theory, MHD waves. We're focusing on some really incredible recent source material, a combination of complex modeling and these groundbreaking high-resolution observations that seem to provide the strongest evidence yet for a specific type of wave driving this heating. Exactly. And to really get it, you need to understand the wave toolkit available in the solar plasma. When you have plasma mixed with magnetic fields, you basically get three main types of waves. You've got the slow and fast magnetoacoustic modes. They rely on both gas pressure and magnetic forces.
Okay. And then there's the third one, the key one for today.
That's the Alfvén mode.
Yeah.
The Alfvén mode is, it's different. It's primarily supported by magnetic tension alone. Think of it like plucking a guitar string, but the string is made of magnetic field. And it's largely incompressible. It doesn't really squash the plasma much.
Right, so it's like a ripple along the field line. So what happens when these waves travel up into the sun's upper atmosphere, where the magnetic field really starts to dominate everything, that low plasma beta environment?
Well, that changes the game completely. When magnetic pressure just overwhelms the gas pressure, the wave propagation becomes highly anisotropic. It means the waves get channeled, essentially. The Alfvén waves, and also the slow modes, they strongly prefer to travel along the magnetic field lines. They find it very difficult, almost impossible, to propagate perpendicular to the field.
So they're guided. If you imagine these waves inside, say, a magnetic flux tube, like a bundle of field lines, do they look different?
They manifest in distinct shapes, or modes, yes. We usually talk about two main ones based on their geometry. They're azimuthal, wave number n. First, there's the $1 mode. We call that the sausage mode.
Sausage mode, okay.
Yeah, it involves compressions and rarefactions along the tube, like you're squeezing and stretching it periodically. And that creates density changes, so you'd see it as areas getting brighter or darker in observations.
Makes sense. And the other main one?
That's the $1 mode, the kink mode. This is more of a large-scale thing. The whole flux tube basically sways side to side, like a guitar string vibrating back and forth. Its central axis moves.
Okay, a kink mode. And the idea is these are kicked off from below by all the churning in the photosphere.
That's the prevailing theory, driven by photospheric motions, convective flows, maybe swirling motions in those dark intergranular lanes. And the energy gets funneled upwards along these magnetic pathways.
But wait a second. If the kink mode is just the whole tube swing, that sounds like a big, relatively slow movement. How could something like that dissipate enough energy fast enough to heat the corona to millions of degrees? It seems inefficient.
That's a fantastic question. And it's exactly why this was such a puzzle for so long. You're right, the large-scale kink mode just by itself isn't very good at direct heating. It's too coherent, too large scale. The real key, we think, is when that large swaying motion transfers its energy into smaller scale, more complex motions, like the torsional Alfvén wave, which is an $1 mode, but it's a twist, not a squeeze.
Okay. So the kink wave sort of feeds energy into this torsional wave.
Potentially, yes, through mechanisms we could discuss. But actually seeing that small-scale torsional motion directly in the corona, that was extremely difficult. For years, many detections thought to be Alfvén waves were later re-identified as just the kink mode because its signal is often stronger.
Until recently. That brings us to this breakthrough, October 2025 you mentioned, and the telescope that made it possible?
Yes, the Daniel K. Inouye Solar Telescope. DKIST. It's a game changer. 4-meter aperture, incredible resolution. Using its cryo-NIRSP instrument, they got this ultra-high resolution spectroscopic data. They looked at a specific iron line, iron the 30, in the corona. And the data definitively showed that these small-scale torsional motions are, well, they're common, they're prevalent. They exist right alongside the better-known kink motions. It wasn't just kink waves up there.
That is huge. Okay, so the kink mode is the whole tube swaying. You see that as the tube's position changing, right? A bulk displacement. How did they pin down the specific signature of this twisting torsional Alfvén mode? What was the giveaway?
It all came down to the Doppler velocity pattern across the tube. Think about it. If the tube is twisting, one side of the tube is rotating towards you at any given instant, while the opposite side is rotating away from you. So you measure the Doppler shift. One side shows a blue shift moving towards, the other shows a red shift moving away. This very specific pattern, this out-of-phase red-blue asymmetry across the flux tube, that's the smoking gun for the torsional Alfvén wave. It's not just the whole tube shifting velocity together.
Got it. That twisting signature. Very clever. And once they isolated this and did all the corrections, because observing these things is messy, right? Line of sight effects must blur things.
Oh, absolutely. Line of sight integration is a major challenge. It tends to average out and mute these small-scale velocity signals. But once they carefully accounted for those effects, they estimated the mean wave amplitude for these torsional modes. It came out to be around 19.5 kilometers per second.
19.5 kilometers per second. That's a pretty vigorous twist.
It is. It's definitely energetic enough to be a serious contender for heating. It gives us confidence.
Okay, so the energy is there in the motion. The absolutely critical question then, is the energy flux carried by these waves enough to actually power the corona, to pay that energy bill we talked about?
Well, the simulations are very encouraging on that front. They suggest that high-frequency torsional Alfvén waves, the kind with periods less than about 50 seconds, which we see signs of in the chromosphere, carry plenty of energy. For example, in the chromosphere, the simulations show they can carry something like 104 malatext WM2.
Okay, 104 order 4 watts per square meter.
Yeah.
How does that compare to what the corona needs? You said earlier, 104 to 106 sextinus ergs, that translates to.
Right, the maximum needed for the inner corona, that 106 decal text erg, that's about 103 text ander 2.
So they're carrying maybe 10 times the maximum needed energy before they even get to the corona proper?
Exactly. And even when you factor in that some energy will be reflected back down when the waves hit the sharp density and temperature jump at the transition region, the models show they still retain roughly 103 hours text to Venus 2 entering the inner corona, which is right in the ballpark needed to compensate for those radiative and conductive losses. So the energy transport mechanism looks, well, viable. It seems to work on paper, and now we see the waves are there.
Okay. The waves are the couriers. They've got the package. The energy is sufficient. That leaves the final piece, dissipation. How does the wave energy, this kinetic and magnetic energy of motion, actually turn into heat? What stops the wave?
Right, the conversion mechanism. We mainly look at two related processes. The first is called resonant absorption. This happens because flux tubes aren't perfectly uniform. They have boundary layers where the density and magnetic field change rapidly. This inhomogeneity allows energy from large-scale motions, like the kink waves swaying the whole tube, to be efficiently transferred or coupled into localized small-scale motions within that boundary layer, specifically into these azimuthal Alfvén waves, which are essentially torsional motions confined to that layer.
Ah, so the big wave dumps its energy into smaller, more localized twists at the edges, like the energy gets focused.
That's a good way to put it. The energy cascade starts, and then phase mixing often takes over. Within that resonant layer, neighboring magnetic field lines oscillate at slightly different frequencies because the Alfvén speed varies across the layer. They gradually drift out of phase, creating increasingly sharp gradients between adjacent field lines. This effectively shrinks the spatial scale of the motions right down, making it much easier for viscosity or resistivity friction, essentially to kick in and turn that motion into heat.
So resonant absorption starts the process. Phase mixing shreds the energy down to tiny scales, and then heat.
That's the basic picture. And simulations even show interesting effects from just the sun's gravity. The density stratification can actually cause the wave amplitude to increase initially as it travels upwards into less dense regions, but eventually this resonant damping becomes dominant at higher altitudes. So you might see the wave amplitude peak somewhere, say, 45 million meters up in one model before it finally starts to decay and deposit its energy.
This all sounds pretty convincing based on what's called ideal MHD, right? Where the plasma and magnetic field are perfectly locked together. But the sources remind us, the lower solar atmosphere where these waves get started. It's not quite so simple down there, is it?
No, it's definitely not. That's a critical complication we're still grappling with. The lower atmosphere, the photosphere, the chromosphere, is only partially ionized. Down in the photosphere, the plasma can be mostly neutral atoms, maybe only 0.1% ionized.
99.9% neutral. Wow, how does that affect things?
Well, it means the magnetic field doesn't have a perfect grip on the gas. You get what we call non-ideal plasma effects. Things like ambiopolar diffusion, where the neutrals kind of drift through the ions under pressure gradients, and the Hall effect. These effects essentially introduce friction between the charged particles, which feel the magnetic field, and the neutrals, which don't directly. It means the magnetic field lines can start to slip relative to the bulk gas motion.
Which sounds like it would dampen the waves or make it harder to generate them efficiently in the first place?
Exactly. It can dissipate some of the magnetic energy low down before it even gets properly launched towards the corona as a coherent wave. It suggests that our simpler ideal MHD models might be, well, too optimistic about how much energy actually makes it out of those lower layers. We need more complex models incorporating these partial ionization effects.
Okay, so stepping back then, what's the big picture takeaway from all this recent work?
I think the key synthesis for you, for everyone listening, is that seeing both the kink modes and these torsional Alfvén modes simultaneously, with the clarity DKIST provides, it gives us really strong empirical validation for the wave heating idea, much stronger than we've had before. It showed the energy is flowing upwards in these specific magnetic waveforms continuously.
We've got the waves, we've got the energy budget looking plausible, but there's still a big piece missing, isn't there? We haven't actually seen the plasma get hot because of the waves. We haven't observed that final conversion step directly.
That's the final frontier, observationally speaking. And it's incredibly subtle because wave damping is not quite the same thing as wave dissipation. Damping just means the wave motion decays, it gets weaker. Dissipation is the actual conversion of that wave energy into thermal energy, into heat. And in the corona, the plasma is extremely conductive, which ironically makes thermal dissipation very inefficient.
What do you mean by inefficient? It takes longer.
Much longer, potentially. The time scale over which the energy actually turns into heat can be significantly longer than the time scale over which the wave's coherent motion disappears. For example, under typical coronal conditions, high magnetic Reynolds number, we might observe the wave damping out in, say, 13 wave periods. The motion smooths out relatively quickly, but the theoretical dissipation time for that energy to actually manifest as increased temperature could be more like 170 wave periods. That dissipation sim 110 of 5.
Wow, okay. So the motion dies down fast, but the heat gets deposited slowly, maybe spread out, making it really hard to spot that temperature rise definitively linked to the wave passing.
Precisely. It's a major observational challenge. The heat signature is likely weak and diffuse.
Okay, that is the challenge. But we can trace the energy back, right? The waves start down low. You said they're linked to photospheric motions, convection, these swirling flows or vortices people observe.
Yes, the energy ultimately originates deep down in the sun's convection zone, that churning layer beneath the surface. And the strong implication from these torsional wave observations is that it's likely the horizontal motions within that convection, the sideways sloshing and swirling, that are most effective at generating these incompressible, twisting Alfvén waves.
So here's maybe the final thought for you to ponder. We can now, with more confidence than ever, follow the likely path of energy from the deep convective churning up through the photosphere, generating these specific torsional waves, which travel along magnetic field lines into the corona, carrying enough energy, where they eventually dissipate through complex processes like resonant absorption and phase mixing. The chain is almost complete, but the challenge now is twofold. Precisely, how does that deep conductive energy get converted into these specific wave modes at the source? And can we finally catch that elusive signature of the wave energy actually turning into heat high up in the corona? What is that final trigger, that definitive observational proof that connects the sun's deepest churn to its highest heat? That's the puzzle still waiting to be fully solved.